Today we're going to talk about the natural base e. The natural base e is a special number, just like pi or I. It's also irrational. It's roughly 2.718281828. Leonhard Euler discovered it. It's used for compound interest. Leonhard Euler discovered that if you continually added together 1 over 1 factorial plus 1 over 2 plus factorial plus 1 over 3 factorial, etc., and continued to do that forever, that sum would come closer and closer to e, but would never reach e. And so that's where our e value comes from. Like I said, we call it the natural base e. It's the base of natural logarithms, which we'll work with later. So if we're asked to simplify the expression, since e is just a number, we can treat it like a number or like an exponent. So the same rules apply. So if we have numbers with the same base and we multiply them together, we can add the exponents. So e to the 7th times e to the 4th is simply e to the 11th. Because we simply added 7 plus 4. So in our second problem, we would do 2 times 6 is 12. And then we have e to the negative 3rd times e to the 5th. Once again, we can just add our exponents. And so we get e squared. So the answer simplifies to 12e squared. Same rules apply. So 24 divided by 4 is 6. When we divide numbers raised to a power, when we divide numbers that have the same base, we can simply subtract the exponents. So e to the 8th divided by e to the 5th is e to the 3rd. With this fourth problem, all we have to do is remember to distribute our cubed. So we have 10 cubed times e to the negative 4x cubed. 10 cubed is simply 1,000. E to the negative 4x cubed is e to the negative 12x, because power to power we multiply. We don't want negative exponents, so this simplifies to 1,000 over e to the 12x. Now, yesterday we talked about exponential growth and decay functions. We're going to talk about natural base functions that also grow or decay exponentially. So these are the form y equals a times e to the rx. So e is going to be our base, and so that's not going to determine our growth or decay anymore. Now it's our exponent. So if our r is greater than 0, if our exponent is positive, it's going to be exponential growth. And if our r is less than 0, if our exponent is negative, it's going to be exponential decay. So this first one asks to identify if the function is exponential decay or growth. This would be a function of exponential decay, because our exponent is negative x. It then asks us to graph the function, so we're just going to make a table of values. So our easiest is to start with x equals 0. 3 times e to the 0 is simply 3. If we use 1, that gives us 3 times e to the negative 1. Now we can simply plug this into our calculators. 3, our e button is second ln, so 3 times e to the negative 1, and that gives us roughly 1.1. So this is roughly 1.1. If we plug in 2, we get 3e to the negative 2nd. Once again, we can plug that in our calculators, and we get 0.4. If we do negative 1, we have 3 times e to the 1, which is simply 8.2. And if we plug in negative 2, we get 3e squared. 3e squared is 22.2. So we can graph this. We have the point 0, 3, 1, 1.1, 2.4, and then negative 1, 8.2, so that's going to be up here, and negative 2, 22.2, so that's going to be way up here. And so we can graph, and we remember that our exponential growth or decay functions are not going to cross our x-axis because e is a positive number, so raised to any power, it's going to be a positive number. So it's not going to cross our x-axis. It's just going to get closer and closer to it. This next problem is an example of exponential growth because our exponent is 4x, which is positive. So once again, we can create a table of values. We're going to use 0. 2 times e to the 0 is 2. If we use negative 1, we get 2e to the negative 4, which is roughly 0.04. And if we do positive 1, we get 2e to the 4th. 2e to the 4th is 109.2. So as we can see, this is going to jump very quickly because our exponent is 4x. So we're just going to graph it based off of that. So negative 1.4, 0, 2, and then 1, 100 is way up there. So we can see that, once again, it's not actually going to touch the x-axis, it's just going to get closer and closer to it, and it's going to continue up the y-axis pretty quickly. All right, so we can use our natural base log, our e, in order to figure out with bank accounts if the interest is compounded continuously. So that'll be the key word you're looking for here, continuously. Previously, we worked with interest that was compounded yearly or semi-annually or monthly, but this is interest that's compounded continually. So once again, our amount in our account is our A, that's our total. The amount of time in years, T, once again, in years. Principal amount is P, remember that's how much money we start with, how much money we put in. And then our annual interest rate is R, and remember that's in decimal form. So if it's 6%, it's 0.06. So with this first problem over here, you deposit $4,000 in an account that pays 6% annual interest, compounded continuously. Remember, continuously is our key word. What is the balance after 1 year? So since it's continuously, we know we can use the equation on our left. So our total equals our principal, which is 4,000 times e to the r. Our rate is 6%, which we would write as 0.06. And then our years is simply 1. So we're going to do 4,000 times e to the 0.06. And we get $4,247.35. You and your friend each have bank accounts that earn annual interest that is compounded continuously. Remember, continuously is our keyword to use the equation from before. The balance A in dollars of your account after 2 years can be modeled by the function A equals 4,500 times e to the 0.04t. The graph shows the balance of your friend's account over time. So the equation represents your account and the graph represents your friend's account. We're going to name our friend Bob. Solid name. All right. So which account has the greater principal? So Bob, we'll start with our friend Bob. We can simply look at the graph. Obviously the principal would be how much money was in there at 0 years. And so at 0, we can see that our y value is 4,000. So Bob started with $4,000. Now, as for yourself, remember your bank account is modeled by the equation given. So you started with $4,500 because that value in our equation is our principal value. So you started with more money than Bob. The next question asks us, which has a greater balance after 10 years? So let's look at our graph to see how much money Bob has after 10 years. So at 10, we can see that he has roughly $7,000 $300, roughly, just reading off the graph. Now, as for you, in order to figure out how much money you have after 10 years, we're going to need to plug 10 into our equation for t. So remember, A equals 4,500 times e to the 0.04 times 10, right? Because it's 10 years. So we can plug this in our calculator. Note that 0.04 times 10 is just 0.4. So we can do 4,500 times e to the 0.4. And we get that you had $6,713.21 in your account. So after 10 years, Bob has more money in his account than you do, even though you started with more money than Bob.